Okay. It says something about quantum numbers in there somewhere. Okay. For your class, I'm actually going to have a discussion and teach you the quantum numbers. For the other class, we're going to do more of the letter coding. You're going to do both. You're going to do both the letter coding and the quantum numbers. They're just going to do the letter coding. That's okay. Ooh, cheater. He's a cheater. Okay. So anyway, we're going to use this thing called an address analogy. There's actually two different ways we're going to talk about this. There are 4 quantum numbers, which means there are 4 parts to locating where an atom might, or an electron might be in an atom. Okay? Now the analogy, let's imagine this. Let's say I was trying to find Will. I don't know why, but I was trying to find Will. And I'm out in Colorado. Well, where is the next best place? If I run into somebody that says, oh, I know Will. He's in Ohio. He's in Ohio. I'm like, oh, awesome. That narrows it down. It's better than looking over the whole country, wouldn't you agree? So it narrows it down. He's in Ohio. So I come to Ohio and start looking for Will. What are my chances of finding Will? Yeah, very good. But better than I had looking out in Colorado, would you agree? Okay, or Canada for that matter. So anyway, so I go to Ohio, and I'm roaming around Hawaii. I'm up in, like, say, Bryan, Ohio. Anybody know where Bryan, Ohio is? Yeah, that's where I spent my first 10 years teaching. But anyway, so it's about 3 hours from here. You can't get there from here. So now I'm up in Bryan, Ohio, and I'm roaming around my old neighborhood, and I'm saying, hey, do you know Will? Have you seen Will? Like, I think he's in Delaware. I'm like, where the heck's Delaware? And so I'm like, okay. So I come down to Delaware. I've got 2 parts now, right? Ohio and Delaware. What are my chances of finding him now? Better, but still not wonderful, right? So, as I'm roaming around Delaware, I'm out in Troy Farms, kind of poking around out there. Don't find him anywhere out there. So then I go to name another place. I don't know the places in Delaware. The Y.
That's a place.
Where are some other locations?
Carson Farms.
Carson Farms. So I'm walking around Carson Farms. Hey, you know what? I think he's over on Euclid Avenue. Oh, okay. So now I come to Euclid Avenue. Do you guys know where Euclid Avenue is? Yeah. Oh, okay, good. Some people don't know that. So now what are my chances of finding Will? Better. Pretty good, right? But still, Euclid Avenue is a relatively long street. So I'm roaming around, and finally I find him. Where is he? 289 Euclid Avenue. Now, as it turns out, only one person's allowed to be here at a time. The rest of you don't count. Okay? We'll get more into that later. But only one electron is allowed to exist at any one address, all 4 parts of the address at any one time. That'll happen maybe today, maybe tomorrow, not sure yet. Anyway, so there we are. Those are the 4 parts. Now, how are we going to do that with electrons? Well, you already know one of the pieces of the address. You've known that since approximately 8th grade, possibly before. The energy levels. Okay? So, first energy level, Ohio. Second energy level, California. You know what I'm saying? So the energy levels are the minimum amount of information we can have. Something that has probably never been put across to you yet, and if you look over on at the bottom of page 107, you'll actually see a relatively accurate dispersion of the energy levels to each other. They're not evenly spread out, as you can see, right? In fact, there's a pretty large gap between the first energy level and the second energy level, would you agree? And then as you go further and further from the nucleus, what happens to the distance between the energy levels? Starts getting smaller. There's an actual relatively easy explanation for that, and if I, only one person wrote that down. Maybe two. Hold on. I didn't think you would have. No. No, you wouldn't have either. You would have. But then, no, you did. I knew you would have. The whole Coulomb's law thing is the explanation for that. For those of you that bothered to write down Coulomb's law. What is the force of attraction related to?
Oh, I wrote that down in here.
Okay. Oh, you wrote it down somewhere else.
Yeah.
Okay, that's fine. What is the force of attraction or repulsion, depending if we're talking about like charges or unlike charges? What's it relative to? Well, I know what the equation is. Well, I get you do. You're not sure how to put it into words yet. Okay, it's related. It's directly related to the product of the charges, the two Q's, and indirectly related to the square of the distance between them. I'll rewrite this so you guys can see what I'm talking about. I know we talked about this. There's a reason we talked about it. It's going to guide everything we do for the next 4 chapters. How about that?
Is that a decrease?
It is.
I had an R.
Well, I put R.
Is D more correct?
Well, there's the nucleus. Here's an electron. What is this? Or distance. You know what I'm saying? There's a distance between the two pieces, which is the radius of the atom. Anyway, and that value is squared, okay? Where I'm going with this is, would anyone like to take a stab as to why the distance between the energy levels gets smaller and smaller the further away you get from the atom?
The attraction is less. The nucleus is bigger?
Meaning?
There's like more protons.
Got it. So, let's imagine this is the protons and this is an electrons. It doesn't matter, but let's imagine it. This value of Q is going to get, the further we get away from the nucleus, larger and larger and larger and larger, right? More protons, wouldn't you say? I don't know if you guys know that the periods match up with the energy levels yet. Have we talked about that? Okay, well, that'll all come in handy really soon here, okay? But the periods are the energy levels. So, first energy level, how many electrons are you allowed to have? 2, hydrogen and helium. Second energy level, how many electrons are you allowed to have? 8. 1, 2, 3, 4, 5, 6, 7, 8. See where I'm going with that? Wait, it gets way better. It gets way better. But for now, you guys okay with that, right? Okay, so now, how many protons here? 2. How many here? 10. How many protons here? Watch this. 36. 54. You know what I'm saying? So this value keeps getting larger and larger and larger. And so for each electron, they're being held even more tightly because, remember, it's the product of those two numbers. I'm just saying that's what's going on. Okay, there's a reason for that decrease in distance between the energy levels. Okay, next. Oh, not there yet. Okay, we are flipping over, page 3. We're going to start learning how the electrons are arranged in the atoms. We're going to learn the 4 quantum numbers and the actual symbols that go along with that. The first quantum number is one you've already known for a long, long time. It's called the principal quantum number. In the parentheses, please write the lowercase letter n. Bahamas?
No.
No?
This is about Canada. I don't know why.
I don't either. Anyway, so as it says, it indicates the distance from the nucleus. You guys have known that forever and ever and ever. Let me see what else I want to say. Oh no, I don't know what I want to say for B. But C, the higher the number, the higher the energy, the further from the nucleus, blah, blah, blah. You guys will see this big blank area off to the right. What I'm going to have you do, don't do it yet, but I'm going to have you reproduce as best as you can in that space. Try to use up a lot of the space. The width is probably a bigger deal than the height. No, I will say that. The width is a bigger deal than the height. Use up almost all of the width. You know, height, maybe half the page would be plenty. Might even be able to get away with a third of the page, depending on how small you write. There's another analogy. Besides the address analogy, I'm going to use a ladder analogy. I mean, if you think about that little diagram that was on page 107, it's kind of like a ladder. It's just that the rungs aren't equally spaced. Is this your playbook?
Yeah, my gig book.
Gig book. Now, obviously, where do we put ladders usually when we're going to use one? On the ground. Okay, so the ground is going to represent the nucleus. Oh, I know what the B is. The value of N can be any positive integer from one through infinity. So theoretically, and I think we mentioned this the other day, the electron could be anywhere, any electron for an individual atom could be anywhere in the universe. Now, the probability of that happening is really, really small. That's why we go with that 90% probability region. But technically, it could be anywhere. So the values of n are one positive integers through infinity. All right. Okay, there's not much more we can do about that because you guys already get energy levels. You've done that for a little while now. Okay, so let's move on to the next one because this is all the brand new stuff. I had alluded to earlier in the class year that each energy level can contain sublevels. Okay, so I'm going to start using two different words interchangeably: sublevel and orbital. They mean the same thing. In fact, even in the same, even in that little number 2, I may have used both. I did. Orbital, sublevel. Now, did I give you guys a split level house analogy yet? Actually, let's not even go there. Do you guys know what a split level house is? Anybody have to live in a split level house? We're on the same floor. You still might have two different kind of levels, like 2 or 3 steps up to like another room or something like that. Here's another analogy. If you look right out here, what floor are we on in the building? First floor. If we go down the math wing or the old math wing, what floor are we on? The first. Are we at the same level? No, because we've got those 3 or 4 steps out there. Would you guys agree? Okay. So even though we're on the first floor, we're at there's 2 different levels. And if you go down by guidance, a very similar kind of thing down there too, right? Okay, still on the first floor, 2 different levels. So that's what we mean by sublevels. We're going to find out really shortly that after the first energy level, each subsequent energy level has 1 or more sublevels associated with it. Okay? We'll get there here in a second. So now I'm on to something, and this is called, I called it the orbital quantum number. In your book, I believe they're calling it the angular momentum quantum number. You look at a third book, it might even have a different name for it, okay? But what this is referring to are the different sublevels. This is where it starts getting fun for us. Hold on. Oh, yeah, that's not going to work out. We'll find out why here in a second. Well, as I said, it designates the shape of the sublevel. The shapes are letter-coded. Here are the shapes and their codes. And I think it says something in there in ascending energy, right? So, we have an s orbital, which is typically somewhat spherical. We have a p orbital. For lack of a better word, we're going to end up calling that a dumbbell shape. You'll see why here in a second. We're going to have a d orbital, which we are not going to name, because there's really no good name for that. And we're going to have f orbitals. Once again, also, we're not going to name that because it's impractical. You'll see why, maybe. All right, so even within an energy level, we might have one or more of these sublevels, and these are also listed very similar to the energy levels in ascending energy. Okay? Now's when I'm going to start doing quantum numbers. Let's talk about E real quick. The number of sublevel shapes is equal to the value of the principal quantum number. So, at n equals 1, how many sublevel shapes are we expecting? 1. Which one do you think it might be? The S. It turns out all of the energy levels have an s orbital. And it's lowest in energy at that energy level. At n equals 2, how many different shapes do you think? 2. What do you think they're going to be? S and P. Now, do this where I do it and don't do it anymore. Go up a little, go over and up just a little bit. Very similar to that. And then do the same thing for both the third and the fourth energy level. At n equals 3, how many different shapes? 3, S, P, and D. Please do not do anything until you see me do it. So the first time we're allowed to run into a D energy or sublevel is at the third energy level. We're going to go up and over a little bit. And I'm going to do the same thing up here at the fourth energy level, up and over a little bit. And then obviously at the fourth energy level is where we're going to run into our first F orbital. It is going to be up a little bit more and over even more. See on that? That's all right, you didn't know. You can either change it, but since it's in pen, probably not, which is why, one of the reasons why I have all these blank pages. But whatever. All right, so now, that's all the letter coding stuff. This is what all my regular chemistry kids are going to get, blah, 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 blah. You guys get the bonus material. Well, we already know. Did I give you a... I did not. There should be some parentheses right next to where it says orbital quantum number or not. No? No. Okay. Well, you already put something in there. One way or the other, very similar in position to the where I put the parentheses for the principal quantum number. If you could put some parentheses near the orbital quantum number and put a lowercase script L. I'll write it up here if you're not quite sure what to do with that. A lowercase script L. It's going to look like that. That's the symbol for the orbital quantum number. Now, we've already done n, where we said that n can equal 1, 2, 3, through infinity. The possible values for L are as follows, and this is inclusive. Possible values for L are 0, 1, 2, 3, through n minus 1. I'm going to go through some examples, so don't get too distraught yet. For example, If n equals 1, what are my possible values for L? Well, as high as we can go is n minus 1. If n is 1, what's 1 minus 1? 0. By the way, I did this on purpose. You guys all have your little note packets there, nice and folded up neatly so they don't take up a lot of space and you can write things down pretty easily. However, you'll notice I wasted trees, but I didn't because we have all these blank pages right next to them. If you guys want to add this, if you're starting to run out of room, you can put stuff over there is what I'm saying. What if n equals 2? What are my possible values for L? Remember, it's 1, 0, and 1. Okay? See where I'm going with that? Just for fun, if n equals 4, what are my possible values for L? 0, 1, 2, 3. Would you agree? Okay. Here's the fun part. Each of those values for L represents a shape. Would anyone like to take a stab at to what shape L of 0 would be? A sphere. An s orbital. An L of 1 would represent a p orbital. An L of 2 would equal a d orbital, and an L of 3 would be an f orbital. You'll see, listen, for about a day to a day and a half, this is all going to seem crazy. It's going to flat out seem crazy. In fact, one of my students a long time ago, after I was doing all this stuff and putting things together, the whole class was pretty much sitting there kind of like you guys are right now, except with a little bit more stunned look on their faces. And I said, does anyone have any questions? And the whole class continued to sit there like... And a couple of minutes later, a kid finally raised his hand, and I said, Andrew! That's who it was. I remember his name. This is 24 years ago. I go, Andrew, great, what's your question? Miss Lehman, are you just making this up as you go along? It's going to seem that way for a little while. And then all of a sudden, it's just all going to come together. You go, oh, wow, that's cool. So, anyway. I think I'm done. Yeah, so far we're done with orbital quantum number until we actually start doing things with it. Now we're going to move on to the magnetic quantum number. Once in a while you'll see that written as the azimuthal quantum number. Your book calls it magnetic quantum number. Okay, so we are going to use the symbol M sub L for that one. What the magnetic quantum number does is indicates the position of the individual sublevels about the 3 axes in space. What are the 3 axes in space? The Cartesian coordinates. X, Y, and Z. Awesome. I'm trying to pick students who are going to be able to play the game pretty well. Could you, you guys see this? Could you please touch the x-axis? Nicely done. Did everyone see where she touched? Touch the x-axis. That's not the x-axis. She touched there. Where's the x-axis? There you go. Did he touch a different thing? Why? Yeah, relative. Yeah, it's a perspective thing, right? So, if you're an atom, what are the three axes? It doesn't matter. You know what I'm saying? Depends on where you're coming from. So where I'm going with this is we need a way to communicate with each other so that we know where we're talking about. So we'll say X, Y, and Z. But, you know, to the aliens that live in a different universe, coming, of course, you know, to Earth, what's X, what's Y, what's up, what's down? You know what I'm saying? Back when I used to teach freshmen, I always did this. It was so much fun. I'd have a globe. There are various reasons why I would need the globe, but I'd pull out a globe, and every time I pulled it out for the first time, I'd always have it, what you guys would say, upside down. And I'd be going through whatever discussion I was having, and, you know, these kids would be sitting there with their hands up, and their hands up like they're being cool, like, oh, look, the teacher's stupid and doesn't know that the globe's upside down. And finally I go, yeah, what's your question? Hey, your globe's upside down. No, it's not. And I'd keep on going. I'm like, yeah, it is. It's not. I mean, again, if you go back to that whole, you know, aliens come from a different place, what's up, what's down, what's sideways? What's that? Absolutely. Don't you? Okay. I mean, when you guys look into the sky, what do you see at night if it's not cloudy? Stars? You don't see very many stars. Most of that stuff you're seeing are galaxies. Yeah. We are just such a small part of what is out there. It's so fun to think about, isn't it? I just blew Haley's mind a little bit.
Like, it depends on my mood of the day. Like, if I didn't have a good day, I'm just like, nothing matters. We're all just going to die. Like, yeah.
Well, we all are all going to die at some point. Hopefully not tomorrow. All right, moving on. So anyway, the three axes of space, of course, we call the three axes X, Y, and Z. Okay. If you can turn to page 108, you'll see an example at the bottom of page 108. On the left-hand side, you'll see an S orbital represented and how it's oriented about the three axes in space. You'll see a P orbital. You see where I got the dumbbell idea from? Okay. Well, you must be a dumbbell. I'm just sorry. Just kidding. And then you see a D orbital, which kind of looks like a double dumbbell, exactly, except then you look over across on the page on 109 and you'll see that maybe that's not always the case. Okay? Anyway, at the top of page 109, you'll see how those P orbitals are each aligned along one of the three axes in space. The D orbitals, some of them appear to be aligned along the three axes in space, but some of them are like in between, and then one of them is just weird. Right? And your particular book, in fact, there's not very many textbooks that have the F orbitals pictured. I have an example of a textbook that does, and it's not the current AP book. I have to go back to like 3 AP books ago to find one. You can pass this along if you want. You don't have to. I don't care. Chapter 7. Orbitals. Hey, here we go. Here's some F's. Bottom of page 309 are some F's. You'll figure it out. All right, so anyway. So where I'm going with this is each sublevel has more than one, and those are aligned variously about the three axes in space. The question now becomes, how many sublevels are there? And here's how this is determined. The possible values for M sub L, or the magnetic quantum number, are negative L through 0 up to and including positive L. So this brings all kinds of fun into the story. So, if n equals 1, thank you. Here we go. So you mean you can't have negative numbers? Have you seen your grade lately? I'm kidding. That was so easy. That was so fun. She knows I'm kidding, I think. Did you notice?
I had an F in orchestra last week, but that was because I was absent. So.
Oh.
But
Well,
it's all good now.
quit being absent.
Okay, I'll come to be negative. Cool.
With these guys, I do. Anyway.
Physics too, we get it's like it's good now that I know I can build.
Now that you know, you can build off of that. So, anyway, if n equals 1, obviously we already determined that my only value of L would be 0. Now, watch this. What about M sub L? Well, if L is 0, and my only possible choices for M sub L are negative whatever L is, up through positive whatever L is, and L is 0, what's the only thing I can have? 0. It's the only number I can have. Therefore, at any one energy level, how many s orbitals are there going to be? Remember, L of 0 is an s orbital, right? Let me do this. Hold on. Time out. Some of you already have something like that written down somewhere, right? I saw you doing it. Okay? And if we have an s orbital, how many different s orbitals can there be? 1. That's why you'll see 1 s orbital. However, if n equals 2, what are my possible values for L? 0, which is an s orbital, and 1, which is a p orbital, right? What's my values for M sub L? Well, at 0, L of 0, the only thing I can have is a 0. Here we go, Haley. But at L of 1, what are my possible values for M sub L? Negative 1, 0, to positive 1. Or, to put this in perspective, that's the p orbital, right? How many different p orbitals are represented on the top of page 110 there? 3. One of them is aligned along the px, one along the y, and one along the z. X, y, z. Again, right now we're obtaining information. Some of you are keeping up. Most of you aren't. Some of you are like hanging in various levels of understanding. That's okay. We're going to keep pushing, and you guys will keep practicing, and you guys will get better. Just for fun, I want to do this. If n were to equal 3, what are my possible values for L? 0, 1, 2. What are my possible values for M sub L? Well, what does a L of 0 represent? An s orbital. How many s orbitals are there? 1, because that's the only thing it can represent is a 0. At L equals 1. What are my possible values for M sub L? Negative 1, 0, positive 1. This is a p orbital. Px, py, pz. If L equals 2, what type of orbital are we referring to? You probably have it in your notes somewhere, but a d orbital. What are my possible values for M sub L? How many differently shaped d orbitals are there then? Look in the books. What do you find out? There are 5. And just for fun, if L equals 3, what type of orbital are we talking about? F. Anyone want to take a stab as to how many different F orbitals there are that aren't currently looking at that one book? 7. 7. -3, -2, -1, 0. +1, +2, +3. Isn't that kind of cool? I think that was a big step for some of you right there to put things together. And then there's a little blurb at the bottom that says something to the effect that the total number of orbitals per energy level is equal to the square of the principal quantum number. Let's back up a little bit and review and then learn how to apply that. Remember we said N tells us the energy level. It also tells us the number of different energy or orbital shapes. So at N equals 1, how many different shapes? 1. And that shape's obviously going to be an S. At N equals 2, there are 2 shapes. They will be an S and a P. And N equals 3, 3 shapes, N equals 4. Okay, so on and so forth, right? Somebody ask. Josh? Oh, usually this would be a Josh question. If it's not a Josh question, it's an Aaron question. Doesn't matter. Aaron doesn't ask very many questions. It's usually him. It's true, right? Usually there's a question that gets asked at this point. Because what we have done is gotten to N equals 4, and I said how many different shapes, and we said 4, S, P, D, and F. What's that? What about 1 and 4? What? What about more than 4? What do we do after that? For example, at N equals 5, let's answer this question. At N equals 5, how many different shapes? 5. What are they? S, P, D, F. Turns out, from that point forward, you just follow the alphabet. G, H, I, J, K, L. I'm serious. That's what you do. Yeah, I don't. You know what? We don't have to worry about it. We're going to find that out. That's a question, Aaron. Aaron just asked a question. We're going to find out really soon that we don't have enough elements to do that. In fact, we've exhausted all the ones that we need. We'll find that out here in the next couple of days. Okay? Anyway, time out. Let's do this. What are, or how many orbitals, or sorry about that, positions of orbitals, orientations of orbitals, will there be if L equals 4? At L equals 4, how many different orbitals to have a value of L equals 4? 9. -4 through +4, including 0. So you get 9. Are you noticing the odd number thing?
Wait a second, I think I get this now.
There's any number of ways that you can get it, but there's one. Okay, so, all right. Wow, we've done pretty well with this. Let me fill in this, though.
I think the best part is if you like drew arrows between L and such.
Now, here's the deal. I want you, we as a group are going to differentiate between the PX, the PY, and the PZ. Mainly because we're going to be dealing with those a lot in the course of the next few days. However, with the Ds, honestly, I might be able to come up with all of the subscripts there, but I know that I would not be able to match them up with the correct shape. Because it doesn't matter. I don't care. At high school or even first year college, it doesn't matter. Okay? So because of that, for the D's, I'm not going to have us designate XYZ or DZ squared or whatever it happens to be, okay? What we can do is just say, oh, those are D orbitals. And then obviously the same for the F's, because you guys don't even know those. And this, I have a feeling, is a wonderful place to stop for your brains to sit there and take a little time to let that absorb for a little while. Like I said, it's like a day and a half to 2 days where it seems like everything's just really out of whack, but it does all start to come together. Yes. I won't either. Will you just not be here, There's nothing I can do this instant to help you out. I'll see if I can get something posted online for you. They're going to be working on this assignment. I will make sure that ends up on Canvas so that you can at least start looking at it.
Where are you going?
Where am I going?
Yep.
I am going to go, I'll be in the office all day. Yeah, I got ALC. I don't even know what that means. Alternative Learning Center.
Yeah. Wait.
I got in trouble.
Sorry?
No, I'm kidding. I'm going to be in a meeting all day.
I thought you were being serious.
Well, about
Also,
the getting in.
I thought it was American Leadership Conference.
Oh, no. And here's why you don't know what ALC means.
I'm not.
You've not.